analysis of algorithms. We have been dealing with the various algorithms, and computer science is about designing algorithms. It is not learning C language or C++ language or Java, etc. Those are just tools to execute these various algorithms. So when you design an algorithm, we would like to know which is the best case, which is the worst case, and which is the average case, so that our algorithm, we implement it in a very efficient way. So in this lecture, we will go through three cases of analysis: the best, the worst, and the average case. So here we have. So we have three cases to analyze given up. Whenever it's an algorithm, we ask the question, now, what is the best case in this? What is the worst case in this? And what is the average case in this? So this is what we are going to ask whenever we deal with the algorithm. And that is what the study is about: complexity of algorithms. Let us consider this very simple example of linear search. So you, for example, you have an array here of n numbers. N could be 100, maybe just 20 or 1,000 numbers. So I have a few numbers there. And let us ask for the best case. Best case means I search for the number and I get it immediately. Now this is not an ordered list. We have just random numbers are there in random order. Suppose I want to search for 10. That happens to the best case because it's the first. The moment I start searching, because I start searching from the first location to the nth location. So in this case, the best case would be searching for 10, and it is at the first comparison itself. Therefore, the best case time taken would be of the order of 1, of the order of 1. Later we will say is big O of 1. That is the best case. Let us take the worst case. Worst case. The number is right at the end of the list, nth number, maybe thousands or millionth location. That means I have to go through the list again and again, right, starting from the beginning till the end. So I have to do n comparisons. Therefore, the worst case would be therefore of the to search. This is, for example, to search 2 here. It is the nth number. Therefore, the worst case is going to be it takes time. The upper bound in running time to search an element would be of the order of n. That means there are going to be n comparisons, because every time you ask, is a of 1 is equal to 10, or is a of 2 is equal to 2, is a of 3, etc., up to is a of n is equal to 2. Yes, that means I have reached search for the number and it is found. And if the number is not there, I have to go to the whole list and come to the end of the list and say it is not there. So these are the two cases in linear search. The best case is of the order of 1. That means it is right at the beginning of the list. But the worst case would be it is right at the end and it needs n comparisons. Therefore, it is of the order of n. Let us try to find what is the average time. I do not know where it is. So let us check about the average time. Average case would be taking comparing time for each of these moves. So calculate the computing time for all the inputs. Sum of all the calculated values and uh, divide the sum by total number of inputs. For example, therefore, if there are n numbers, to find the first number 1, to find the second number 2, to find the third number 3, etc. So therefore all possible case times, it is 1 plus 2 plus 3 up to n, divided by number of cases, that is 1 plus 2, as you say, up to plus n. So it could be any one of these numbers. That's why I'm saying average case divided by n. So very simple calculation. 1 plus 2 plus n is equal to n into n plus 1 by 2 divided by n. That is going to be n plus 1 by 2. Therefore, to simplify this, I say it is odd. It is of the order also of n. It is also fine. It is of the order of n. Even the average case also is of the order of n, because it could be last one, could be first one, it could be somewhere in the middle. Best case and worst case in searching for a number in a full binary search tree using binary search tree. So let us consider. Now suppose I want to now we have arranged these numbers in the ascending order in a binary search tree. It's a complete tree. Starts with so 5, 10, 20, 25, 30, 40, 50, 60. Now, what is the best case? So, for example, I want to search for 30. 30 is at the root of the tree, and that is the best case because I always start the search with the root of a binary search tree. Therefore, that is going to be the best of the order of 1. What is going to be? Suppose I want to search for 5. Search for 5. So it means I have to ask the question here is equal to 5. I go to the left is less than 30. I go to the left again. I ask whether is equal to 5. No. I again go to the left again. Then I come. In other words, I have got one, two, three, four comparisons. Comparisons are there. Four comparisons are there. And as you see, the height of the tree is 3. Height of the tree or the depth of the tree is equal to 3. So altogether there are 8 elements. Therefore, 2 to the power 3 is equal to 8. 8 elements are there. Therefore, log 2 of 8 is equal to 3. Log 2 of 8 is equal to 3. Therefore, it is going to be log n. Log n. So, in other words, the worst case in the case of binary search tree is going to be log n to the base 2. Whereas we saw in the linear search, it is n. This is log n, that is 3. Log n means it is to the power. If it's, suppose there are 8 numbers, the 3 searches, 3 to the depth of 3 we have to go. And this is a better searching method, better searching method. So best case in this case, in the case of binary search tree is of the order of 1, and worst case, that is searching for the leaf element, is equal to of the order log n, log n. Now here you have got again binary tree, but it's a left skewed tree because all the numbers as you see is 60, 50, 40, 10. So I want to search for 10. How many? I have to search therefore compare 1, 2, 3, 4, 5, 6, 7 times. There are 7 numbers. Therefore, in the case of left skewed tree, binary tree, there are height is 7. Therefore, worst case is 7. Therefore, the worst case is of the order of n. It is like a linear search because it's a left skewed binary tree. Similarly, there may be right skewed binary tree. That also the worst case is going to be of the order of n, the total number of elements present. Again, best case in this case is going to be, for example, I want to search for 60, it is going to be 1. So best case is 1, worst case is n. Why analysis of algorithms is important is the next question. We are going to deal with the analysis of algorithms. Why is that? So let us go through each one of these. So we want to predict the behavior of an algorithm without implementing the specific on a specific computer. Even before we implement, I have got the algorithm, I want to study the algorithm, I want to see how good it is. Therefore, even before implementing it, I can analyze the algorithm and then come to a conclusion whether it is good. We find out the best case and the worst case. That is what. It is much more convenient to have simple measures for the efficiency of an algorithm than to implement the algorithm and test the efficiency. Therefore, analysis will help us even before implementing whether the algorithm is good enough or bad enough when we study the best and the worst cases or the average cases. So it is impossible to predict the exact. Of course, in the analysis, we cannot predict the exact behavior of an algorithm because there are too many influencing factors are there. Analysis is thus only an approximation. It is not perfect. So we know it is somewhere close to this. That is what we are going to say, and but cannot give that it is the perfect answer to a problem. So more importantly, by analyzing different algorithms, we can compare them to determine the best one for our purpose. So this is why we do analysis of algorithm in computer science. So there are some examples here. We will be dealing with those later, but this will give you some idea about the algorithms. So here, for example, we take bubble sort. We have dealt with bubble sort. The best case, of course, in this bubble sort of the order of n. The worst case is of the order of n squared. So worst case is equal to order of n squared. We take big omega. So similarly, selection sort, it is also order of n squared. Insertion sort is also of the order of n squared. But you come to merge sort and heap sort, you find that they are of the order. We want to find out always the worst case. Best case is okay, forget about that. Worst case, what could be the worst case? So you have the order of n log n, and this is of the order of n log n. Merge sort and heap sort. Again, quick sort, as you see, worst case is of the order of n squared. Radix sort and count sort, we are not going to deal with them, but just know it is nk and n plus k, n into k and n plus k. So these are the worst cases in the case of sorting. Bucket sort is of the order of n squared. And we have seen just now that is search, that is binary search, is of the order of log n, which is far better than all these. Of course, these are sorting methods. That is the search method. Search method is of the order of log n, which is very good. So therefore, this is, we will be dealing with all these complexities of various algorithm, and there you will study big O notation, theta notation, and omega notation. We will come to that. Thank you.